Okay, so we're Team Quaker and we developed the MOTUS app. Yeah, so this was me, Jeff, Anthony, and a lot of help from the yeah. Okay, so this is the MOTUS app developed by Jeff, me, and Anthony, and we gave special thanks to Sherry, who helped us out a lot during this.
So an honorary team member for us.
Yeah. So the first question is, have you ever wondered why Dr. Frankie is bald?
No. Well,
it's because of ground motion acceleration maps.
So what are ground motion acceleration maps? Well, this is where we identified a problem. In geotechnical engineering, especially in earthquake engineering, they use maps that will represent approximately what the maximum ground motion acceleration at that location is due to an earthquake. These maps were first developed by Utah State, and they are really basic and very general approximations. There are now new software developments or Excel packages that people have built that allow you to calculate a much more accurate ground motion acceleration. And so we talked with Dr. Frankie, and we figured that this could be a really cool project to make into a web application. So then people could click at any given point where there's fault lines and know exactly what the maximum ground motion acceleration is. This is important because state codes require that structures be able to withstand either 50 or 80% of PHA, which is peak horizontal acceleration, which is another name for ground motion acceleration. So in our app, we wanted to be able to display what those numbers would be for engineers. Any questions so far on what ground motion acceleration is? Okay, let's go. Next one. Hart, take it away.
So we wanted to make an interactive map that used all the faults available, all known, calculates the ground motion acceleration for a user-defined area, finds the maximum earthquake magnitude and uses that in calculating ground motion acceleration. Yeah, we had to dial it back quite a bit because Dr. Frankie was offering Jeff a master's and PhD program to complete this, and he was done with school. So we had to scale it back a bit. So it's not that complex. We're using the simplified equations, and so that can be updated at a later date by those with more experience with the equations.
So we have a basic framework set up for future work to be done to solve this problem. But to create our app, we use two geoprocessing tools: a fault finder, which identifies all the faults within a 60-kilometer radius of the click point, and then the distance finder, which is this model right here, which selects a particular fault and calculates the distance from that click point to the selected fault. This is a little tricky because the near feature doesn't allow you to use a feature set as an input. So we had to use the make feature layer to take our input click and turn that into a point layer. Some of our intermediate calculations, we won't go through all of this entirely, but we had to loop through every single fault line to identify the longest fault. Huh? Oh, thank you. Yeah, let's turn off the lights so we can see that. So once someone clicks, and you'll see this in just a second, it'll create the buffer, and in that buffer, all the faults within that buffer will be selected, and then we had to create a loop that would then identify the longest fault within that buffer. And we use this fault in our next calculation. Once we know where that fault is, we calculate the distance between that fault and the click point. And that distance becomes this variable d. And this variable, along with a lot of other constants, are put into the peak horizontal acceleration equation. And this function will give us the PHA as our output. So let's see that work. And where is Let's move that for a second. Oh. Four. So we'll do a quick demonstration to show how this works. So in our home page, there's the welcome and a little bit of an introduction. You'll go over to the map page, and we'll show 2 points that we will click where we will identify the approximate ground motion acceleration at. So if we click here in Salt Lake City, it's first identifying all the faults around there, and you'll see that the longest fault in that area is part of this segment, or is this segment of a larger fault line that exists in Salt Lake. You'll notice on the left side, it says now click the Calculate PHA button, and that's where our secondary calculations are occurring. And then the PHA, 80% and 50% are displayed on the left side. And if we go now for our second point to Eastern California and calculate our PHA, we'll see again a different horizontal acceleration of 7. We have a little bit of round off error, so that's one problem we're still going to have to fix. But that right there is MOTUS. Thank you.
Tell the audience on the recording to GitHub or bring up GitHub.
And if you would like to view this app and look at our code, come to this GitHub link right here, github.com/Henrichsen/Tethys app-Quaker_MOTUS.